Last time we had talked about the chain rule, the proper way to differentiate composite functions. Does it help us find the derivative y prime if we're given something like this? X to the power of 6 times y to the 7 is equal to sine of x times cosine of y. This type of equation isn't like the types we've seen before. So this is what's called an implicit equation. We need to contrast this versus something called an explicit equation, implicit equation for y versus an explicit equation for y. We have been exclusively dealing with explicit equations where the y has been isolated. Y is by itself on one side of the equation and everything else is on the other. And on that other side, there is nothing to do with a y. Whereas in an implicit equation, which is the type that we've got here in the box, we've got some strange function, phi of x and y, and it's equal to a constant. Here, the y is not isolated. That means it's really difficult for us to try to apply the rules that we normally do in the way that we normally apply them. So we need a strategy to find the derivative in an implicit equation. Now, there's something called the implicit function theorem. And this is heavy-duty math theorem that we aren't going to prove. We aren't even really going to state properly. But it says if you've got some sort of implicit equation like this, it's possible to treat the letter y as some function of x. And once you treat it as a function of x like this, you are then allowed to differentiate. And that's really the theoretical backbone of what we're going to do today. Every time we see an implicit equation, we are going to treat it as though we've got a function y that's dependent on the other letter, the x, and we're going to be able to differentiate it. So the idea is we do not, and I'm trying to emphasize this, we do not try to isolate y in the equation. If we could isolate it, we would, and then we would be back to doing explicit techniques. So when we've got an implicit equation, we are instead going to apply a derivative on both sides of the equation, and then we are going to use the chain rule and others to find the y prime. Now, rather than describing it, I'm going to take that expression that I gave you a little bit earlier, that equation, x to the power of 6, y to the 7 is sine of x times cosine of y, and I'm going to treat y as a function of x. I don't know what function it is. Maybe it's e to the x, maybe it's sine x, maybe it's some weird mystery jumble. And I don't care. What I am going to do is I'm going to take the derivative of both sides of this equation. So now what I'm going to do is just treat the x like the variable, and I'm going to treat the y as some function of that x. So everything here can be differentiated. So I'm going to apply first the product rule because I see this as a product of x. So I'm going to take the derivative of the first times the second plus the first times the derivative of the second, and I'll do the same thing on the other side. Each of the terms is just a differentiable function of the variable x. Now, a couple of these derivatives are actually really straightforward. The ones with the x's in them, this will give me 6x to the 5 times y to the 7. I'm just going to leave these terms alone for the moment. The derivative of sine is cosines. Cosine x times a cosine y plus sine x times the derivative of cos y. This is where the Leibniz notation comes in, and it's not just a basic derivative here. I need to apply the chain rule because effectively what I've got is the derivative of some mystery function to the power of 7. So this y is the inner term, whereas this 7 would be the outer layer of the composite function. Similarly, over here, I need to think of the chain rule. I'm taking the derivative of the cosine of some mystery function. The inner part is the y, whereas the cosine is the outer layer. So the chain rule says the derivative of some stuff or some mystery function to the power of 7 is going to be 7 times that stuff to the power of 6 times the derivative of that stuff. Now, in this particular case, that's just a y, so I'm going to leave it as a y. The same idea is going to get applied on the other side. I'll have a sine x in front, and then the chain rule says the derivative of the cosine of some stuff is negative sine of that stuff times the derivative of that stuff. That stuff here is a y, so I'll just replace it with a y. So we'll have 7x to the 6, y to the 6, dy dx, just for simplicity, I'm going to write as a y prime. And this is how we introduce the derivatives in problems like this. So I'll have cos x, cos y, subtract sine x, sine y times y prime. This turns into an algebraic equation for y prime. So now we just solve for it. And we end up getting two terms that contain a y prime. I'm going to put both of those terms on the same side of the equation. So I will move this one over to the other side. Sine x, sine y times y prime. Everything else that does not have a y prime gets moved to the other side. Now, once that is done, I recognize that I've got a common factor of y prime. I take out that common factor, and I'll be left with 7 times x to the 6 times y to the 6 plus sine x sine y equals all of this other stuff. I don't really care what that other stuff looks like. All that matters to me is trying to get this y prime by itself. And now I can. I just divide through by whatever factor is multiplying that y prime. And at the end of the day, I've actually come up with some sort of expression for y prime. I've got y prime of x is cos x times cos y, subtract all of this stuff, sine x times sine y plus 7x to the 6, y to the 6. In general, it will be in terms of x and in terms of y. I couldn't isolate y in the first place, so there's no reason that I should expect to be able to isolate y in this case. And you might say to yourself, well, this looks awful. What am I supposed to do with this? If you know the coordinates of a point on the implicit equation that we started with, we could take one of the points that lived on that curve, plug in the coordinates, and get the value of the derivative. So up here, I should be a little bit more careful and say this is a function of x and y, and then I could plug them into y prime and get a value. Now, for instance, 0, 0 is a point on this equation. 0, 0 will make this equation true. If I were to plug in 0, 0, I will end up with cosine of 0 is 1, but downstairs I'll end up getting a 0. So it's undefined. Y prime does not exist. This technique that we're using here today is called implicit differentiation. And it's used to find derivatives for or from implicit equations. The value in implicit differentiation is that we are able to use this technique to figure out shortcut derivative formulas for inverse functions.